Okay, great. Thank you very much. Can everyone see my slide?
Yes.
Okay, excellent. So thanks very much. It's a pleasure to get to speak at this conference. And that's correct. I'm going to be talking, so Max and Helmut spoke about the full Holocene, and I'm also a paleoclimatologist, but I'm going to be zooming in on just the 3rd millennium BC. And as you can see from the image, I'm a stalagmite paleoclimatologist, so I'm going to be focusing on stalagmite records. And so just to get oriented, here is an image of the location of different paleoclimate archives that are near or around the Mesopotamia region that I'll be looking at to reconstruct climate during this millennium. And I just want to indicate the difference. So I have here lake sediment records that are in blue diamonds, as well as stalagmite records are in the yellow circles. And just to confirm that everyone can see this slide with the map, because I've had issues with this before. Okay, let me know if you can't see different slides. So now I want to comment on the difference between paleoclimate lake records and stalagmite records for reconstructing paleoclimate. So lake records are, one of their advantages is that they can couple palynological and hydrological investigations. So you can examine both past changes in terrestrial vegetation as well as aquatic ecosystems. However, they tend to, in comparison with the stalagmite record, have poorer age constraints. So on the right-hand side, alternatively, we have the stalagmite record. So these also inside of the calcium carbonate contain multiple what's called climate or environmental proxies. So these are different isotopes or chemical elements that can be related to some degree with rainfall or temperature or other environmental parameters. On a stalagmite, you can do very high resolution sampling depending, I guess, on the sample that you're working with. So the faster the stalagmite grows, the higher resolution record that you can get. And finally, a big advantage of a stalagmite record is you have the potential for very accurate and precise age model because it uses a different radiometric clock. It uses uranium thorium dating as opposed to radiocarbon dating. So just to begin with, I'm going to discuss what the lake records tell us, which is more a background climate, a lower resolution climate information, and then I'll put on top of that my stalagmite record. So here I've pointed out the different lake records that are surrounding the Mesopotamia region, and the Lake Eski-Akigol as well as Lake Van in the north both indicated that in the early Holocene you had wetter conditions, and then as you transitioned into the mid-Holocene, conditions became drier. So that's your overall general background climate. Alternatively, in the Zagros Mountains in the east, you have Lake Sarabar and Lake Maribad, who in the early 2000s came out with research records that showed that there was relatively dry early Holocene climate and wetter conditions in the mid-Holocene. However, these records kind of stand out in the paleoclimate overall record as having alternative results to the rest of the paleoclimate records. And just recently, I was involved with the stalagmite paleoclimate study from Calicor Cave here, indicated also in the Zagros Mountains. And those results show that indeed that there is a wetter earlier Holocene that progressively reduces into a drier mid-Holocene and driest late Holocene. So that somewhat resolves this difference in these lake records. So overall, we tend to think of the earlier Holocene was wetter, and that transition into the mid-Holocene was gradually becoming drier around 5,000, 4,000 years before present. Now introducing my stalagmite record. So this was collected from Golizard Cave in the Alborz Mountains in northern Iran on the southern side of the Alborz Mountains. So you don't get any moisture from the Caspian Sea. All the moisture is coming from westerlies off of the Eastern Mediterranean, or possibly from southwesterly moisture flow from the Red Sea. So this is what the stalagmite looks like. And here you can see I've indicated the black lines where I've sampled age samples. So this is to measure uranium and thorium to get an age and growth rate of the stalagmite. And then down the center, we drill at very small intervals. So here I've sampled at 0.25 millimeters resolution, and those are where you'll measure different paleoclimate proxies for the y-axis of your record. So here's the results from the uranium thorium age samples, and this is really where the stalagmite shines, I guess. So I've plotted, or I've put here in the table both calendar years before present, as well as BCE ages, whatever you're more familiar with. And just, I want to point out here on the rightmost column is our 1 sigma age error. So this is between 20 to 80 years, dependent on the individual sample. So this stalagmite in general, not all stalagmites are created equal, but this one is particularly quote unquote clean. So it has very little to zero thorium contamination from cave dirt or particulates in the chamber, and that will result in a very accurate age if you don't have any of that contamination. The age errors are slightly higher because this sample has a lower concentration of uranium. That's just the nature of this environment. The limestone above the cave happened to have lower uranium concentration, and that will cause your age errors to increase just based on counting statistics. So that's more of a precision error. So if you found a stalagmite that had higher uranium concentration, for example, if it was a regonite versus calcite, then your stalagmite age errors could get down to, in a best case scenario, plus or minus 10 years. But this between 20 and 40, 60 years is still pretty good. And we're very confident in the accuracy because there was little contamination of this thorium, which exists in the dirt. So now if I plot this on what's called an age depth model, I have depth or distance from the top of the stalagmite on the y-axis, and then age is on the x-axis. And so we're going from older in this bottom right corner to younger. Top of the stalagmite is in the upper left. And if the slope is higher, a greater slope means that it's a faster growing in the vertical direction stalagmite. And if the slope becomes more horizontal, that's a slower growth period. So you can see in general, this is what we would call a very fast growing stalagmite. Here in this subpanel, you can see the actual vertical extension rate. So for the majority of the time, it's around 200 to 300 micrometers per year. But there are these periods, one that begins around 4,500 years ago, and then a second that begins around 4,200 years ago, in which the growth rate of the stalagmite really plummets by a factor of 10, so down to around 20 micrometers per year. So that's the information we get just looking at how quickly the stalagmite's growing. But a stalagmite growth rate could decrease not just because of wet or dry conditions, but also it could be due to the drip rate, a change in temperature, or change in drip water chemistry, the saturation of the calcium, for example. So it's a portion of information, but it's not full information. So in addition to this, we want to look at different climate proxies. So here now I've taken the different elements or isotopes that I've measured again along the central growth axis of the stalagmite and plotted it here in a time series on that age model. And so I've measured multiple elements and different isotopes. So here in the upper right-hand corner, just a reminder of how the stalagmite is forming. It's forming from these drip waters that originally dissolved limestone. And I guess before that, were meteoric rainwater. So they contain oxygen isotopes. They contain different elements that was dissolved from the limestone, and they can even contain elements of external aerosol deposits that landed on top of the cave, such as dust or volcanic aerosols. So that all gets into the drip water and then precipitates within the stalagmite. So here I've plotted the two elements or isotopes that really stood out in the record, because in the time series, the variability was really apparent that there was certain events that occurred within this millennium. So in the upper panel is the magnesium to calcium ratio, and in the lower panel is an oxygen isotopic ratio. And I'm going to discuss both of those individually to explain how we interpret that. And again, I just want to show on this x-axis here, we're looking at the third millennium. So it's between 3000 and 2000 approximately BCE. So first I'm going to think about how to explain the magnesium to calcium ratio. So again, that's this upper panel here. So we have a background condition, but there's these periods where they increase to a very large degree above the general background average. And our interpretation is that that could be a signal that's produced from leaching of that magnesium from dust deposits above the cave. And we get that idea because of different studies that have been done on dust events in Tehran, which is very close to our Galizard cave site, which shows that a very large percentage of the dust that's deposited in this area originates from the Mesopotamia region. And in addition to that, here I'm just showing a satellite image which shows these SHAMAL winds and the SHAMAL dust events, which are summer dust events that occur during the dry period of each annual cycle. And this other paleoclimate record, this is a marine core in the Gulf of Oman that shows this large spike. This is a 6,000 year, or approximately between 2,000 and 6,000 years before present record. And you see there's these two peaks in this marine record in both dolomite and calcium carbonate, a weight percent in this marine sediment record. And the scientists of this study, Carolin et al. 2000, determined that these peaks were from dust that originated in the Mesopotamia region, and they determined that based on radiogenic isotope analysis, which confirmed that indeed the source for this dust was the Mesopotamia region. So since this peak is happening around 4,000 years ago, that's coincident in timing with our stalagmite record, and is also a peak in dolomite. And dolomite, of course, is calcium magnesium carbonate. So that would contribute that magnesium element to the stalagmite calcite crystals as they form, originally leached off of those dust deposits above the cave by rainwaters. So we've done a simple mass balance calculation, accounting for the distillation of both the host rock, which is the bedrock that is above the cave, as well as some amount of dust that's deposited on the surface. So if you do a simple calculation, you can produce the increase that's seen in the record from the background conditions, which we get from bedrock samples that we've sampled, up to this increase within these events. And that also agrees with other elements that we've measured in the stalagmite, including strontium and barium, which are part of the limestone, but are not as large a percentage in the dust, because dolomite is a very large percentage magnesium, much smaller percentage strontium and barium. So based on that analysis, we have evidence of this significant increase in Mesopotamia dust activity in both this Iran stalagmite as well as in the Gulf of Oman, with just highlighting that the Gulf of Oman marine sediment core only has a single peak. We see what we believe to be two longer duration peaks. And so our conclusion is that the second peak, which is coincident with the Gulf of Oman peak, is larger in scale, more regional, and possibly a greater increase in dustiness than the earlier peak, which maybe was more local in scale, just affecting maybe northern Mesopotamia and into northern Iran. So that's our conclusion for this upper panel. And so now, in addition, it's always good to have multiple proxies to explain your story. So we'd also like to interpret this oxygen isotope record, which is here in the lower panel. So just looking at it to begin with, the oxygen isotopes are increasing. So on the y-axis here, more positive is up. So we have increasing oxygen isotopes coincident with increasing magnesium calcium ratios, which we are interpreting as a greater amount in either frequency or magnitude of dust events. So oxygen isotopes are generally in this part of the world, so not tropical, mid-latitude. When they vary within rainwater, it's interpreted as an artifact of what's called rayleigh distillation. So what happens is you have your ocean beginning at 0 per mil. So this is just the equation of what this delta O18 means. It's just a ratio of your sample oxygen isotopes. You have the heavier oxygen over the lighter oxygen, and then it's just normalized to a standard. So that's blah, blah, blah. But in general, we're starting off with ocean at 0 per mil. There's a fractionation that happens. And because the heavier isotope prefers to be in the liquid state versus the vapor becomes more negative. And then as you rain out, your initial rainwater begins again at 0 per mil because that fractionation reverses. But over time, because you're raining out the heavier isotope, which prefers again to be in the liquid state, your remaining vapor is becoming lighter and lighter because you're removing all that heavier oxygen. So over time, your rainwater is becoming more and more negative. So the more rain that happens, the lighter, the more negative that oxygen isotope will be. And here's just another way to plot that. So you start off around 0 per mil in your oxygen isotope. And as you're moving away from your moisture source and raining out water, your oxygen isotope is becoming lighter, more and more negative. And then if I put this now on a spatial scale map, the colors here are the oxygen isotopic value of that rainfall. So if you can imagine, you have your rain originating, just in a simple case, in the Eastern Mediterranean, and then it's traveling west across Mesopotamia and then hitting these mountains. As that rainfall happens near the topographic highs, your oxygen isotopes will start to get lighter and lighter. So you can see kind of that shift as you go into the mountains and start to have this rain out. And the idea is if you have a period where there's just overall less rain out happening on that trajectory, then you will move up this curve and your oxygen isotopes will get more positive. So it's just simplest way to think of it is an anti-correlation between oxygen isotopic value and overall rain out along that trajectory. And this is just under modern conditions. Again, this is the cave site, and these arrows are showing the moisture transpoint factor. So it's a column integral of wind multiplied by the specific humidity. So how much moisture is in that column of air above a particular point on the map. So this is, again, the arrows are showing your moistures traveling west to east, eventually making it to the cave site. And then if you look at annually averaged rainfall samples, where you're plotting rainfall amount versus the oxygen isotopic value, then there's a anti-correlation again, so negative slope correlation, where your years that have more rainfall have more negative oxygen, years that have less rainfall have more positive oxygen, with a correlation R squared of around 0.5. So that's about 50% of the variance is explained by this relationship. So with that all in mind, looking again at our plot here, so eventually that rainwater will transfer through the cave and that oxygen will get precipitated within the stalagmite. So now we've gone from rainwater oxygen to stalagmite oxygen. But in the simple case, we'll just imagine that there's no fractionation that occurs in that process. And so now within these periods where, again, I've interpreted that there's greater amounts of dustiness, these oxygen isotopes, again, are getting more positive. And because of that anti-correlation, we're interpreting this as the more positive values indicate less upstream Mesopotamia winter rainout. So with regards to amount of water available in Mesopotamia, if you're having less rainfall in a given year, then there's less water flow in your rivers and possibly as well less rainfall that's making it into the Taurus Mountains and providing the water for both the Euphrates and the Tigris River. And that seems to correspond those periods with periods where we have more dust events. So in summary, this is the full comparison of the Iran stalagmite record. So here's the magnesium calcium, which we're interpreting as dust. Here's the oxygen isotopes, which we're interpreting as dryness upstream, so in the Mesopotamia region or into the mountains, both the Taurus and the Zagros Mountains. And there's evidence of significant increase in dust activity in the Iran stalagmite that is coincident with the significant peak in the Gulf of Oman that was also recording dolomite Mesopotamia-sourced dust. The single peak in the marine record indicates that this later period, so this second gray bar, was more regional in scale and thus characterized by a greater increase in dustiness. And there's other regional paleoclimate records. Maybe strongest is that within the same stalagmite, the oxygen isotope value indicates that overall drier conditions, at least during these periods, relative to the background state of that millennium. And finally, because the magnesium to calcium record has such abrupt shifts, it's very easy to determine the age of the beginning and end of those different events because they're abrupt as opposed to gradual. And so we can calculate the duration of this second event, which comes out to a period of around 300 years. And just to refer to the question in the previous talk, this is the same time span of the quote unquote abandonment of the Tel Ilan site in northern Mesopotamia. So that's very interesting that the duration at least is coincident in timing between the paleoclimate record and the archaeological record. So with that, I'm happy to take any questions on this work.